I want to do another sort of problem where you have to determine the empirical formula of a compound. And here again we're given the amounts, the relative amounts of the elements that we get after you break down the compound. But we're not given the gram amounts, we're given the amounts in percentages. Now, one thing you can kind of do is in the way of a trick is if you add up all these percentages, they equal 100%, 100.00 even, I think, in this case. So that's kind of interesting. So what you could say is that you basically just started off with a 100 gram sample. I mean, this is maybe not exactly what happened, but this is a trick that you can use to actually kind of convert these to gram amounts. So if you had a 100 gram sample, then these actually would be the gram quantities of each of these elements. So then basically this is like the other type of problem where all you've got to do is convert from grams to moles. Okay, and so to do that for chromium, you're just going to take 26.52 grams, and you're going to multiply that by the molar mass, using the molar mass as a conversion factor. So that's going to be one mole of chromium is equal to exactly 52 grams, 52.00 grams, looking at your periodic table. And when you calculate that out, you'll get 0.510 moles of chromium. And then doing the same thing for sulfur, using its amount, you've got 24.52 grams. We're going to assume that 100 gram sample again, total compound sample. So you're going to divide that by the molar, or you're going to multiply it using a conversion factor of the molar mass of sulfur. So that's 32.06 grams. Okay, and when you do that, you'll get 0.765 moles of sulfur. So again, this is moles of chromium, and this is sulfur. Okay, and then we do the same thing for oxygen, which is the most abundant element in this compound, and we get 48.96 times 1 mole over 16.00 grams. And multiplying that out, we get 3.06. So now we're going to do the same thing that we did in the other problem with the empirical formula determination, and we're going to take the element that has the fewest number of moles, which in this case is going to be the chromium, and it is present here. Its molar abundance is 5.10 moles. So then we're just going to divide the other numbers by that. So I'm going to do that down here. So for sulfur, actually that should have just been an S for sulfur, not Sh, so get rid of that. Okay, so for sulfur, we're going to divide 0.765 moles divided by the moles of chromium, which was 0.510. And when we do that, we get a number that's almost exactly 1.5, which is kind of interesting. I'll come back to that in a second, but let's go ahead and do oxygen next. Oxygen is 3.06 moles, and we're going to divide that by 0.510, and when we do that, we get about 6. You can see that 30 divided by 5 is 6. And then of course for chromium, that's just for chromium, that's just 0.510 over itself, so that's just 1. Alright, now the problem that we've got is the empirical formula has to be the lowest whole number, the lowest whole number ratio. And we don't have all whole numbers here. We've got 1.5, we've got 6, and we've got 1. So the way that you solve that is you take all these numbers and you just multiply them by 2. to bump it up, sort of like when you're trying to figure out the least common denominator in a fractional problem. So that just bumps this up to 3 for sulfur, 12 for oxygen, and 2 for chromium. So that means that the empirical formula is just going to be Cr2. You always put the cation first. So Cr2, and then S3 and O12. Now that's a good enough empirical formula. But you can kind of look at this and you can see that if you look at the sulfur to oxygen ratio, it's 1 to 4, 1 sulfur to 4 oxygens, which we know is sort of the formula for a common polyatomic anion. So that will most likely convert out to SO4, which is the sulfate. That's the 1 to 4 ratio, and since this is all multiplied by 3, that would be that. So this would actually be then probably chromium 3 sulfate. Okay, that's it.